Where does Sherwood hide his unit is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video explains the basics of dimensionless numbers. The companion video, What the Schmidt Examples, discusses examples of dimensionless numbers used in chemical and thermal principles. This video, Where does Sherwood hide his unit, discusses three related concepts. The first is that of a dimensionless number or dimensionless group, something that finds frequent application in chemical and thermal principles and other branches of engineering. Next is dimensional homogeneity in an equation. We'll discuss what that means. The final principle is that the argument to any transcendental function has to be dimensionless. In other words, it has to be a dimensionless number and what the implications are. Concept 1. Dimensionless numbers. So engineers often have to do a lot of experiments and try to determine relationships in an empirical fashion. Over the years, they have tried a number of ways to reduce the number of measurements they have to make and get the maximum information they can out of their measurements. The most popular way to cut down on the number of variables that need to be correlated is to use the Buckingham Pi theorem to create dimensionless numbers or groups. If you haven't yet learned Buckingham Pi, you will sometime during your engineering education. The Wikipedia article on Buckingham Pi is an excellent place to review. The link is in the video description. Basically, as long as you use a consistent set of units, it doesn't matter which set of units you use. The dimensionless numbers will calculate to the same value. The most famous dimensionless number is the Reynolds number. The Reynolds number is the fluid density times the fluid velocity times a characteristic length, such as the diameter of a pipe, and divided by the dynamic viscosity, mu. Mu is a measure of how slippery or sticky a fluid is. Honey and molten glass have high viscosities. Room temperature air and liquid helium have low viscosities. The Reynolds number can also be calculated as the fluid velocity times the characteristic length divided by the kinematic viscosity, nu. The kinematic viscosity is the dynamic viscosity divided by the density. The Reynolds number is a measure of the relative importance of momentum given by the velocity times the density to the viscous force given by the ratio of the viscosity to the diameter. Almost all dimensionless numbers express the relative importance of two different engineering quantities. For example, the Sherwood number is basically the ratio of importance of convective transport to diffusive mass transport. If you're actually curious, the definitions for convective and diffusive mass transport are given on the webpage and the links in the description. Buckingham Pi is a formalized way to find dimensionless numbers or parameters. For the DOFPro videos and websites, we will use dimensionless numbers that someone else has found. The second video in this set, What the Schmidt Examples, will discuss many of the dimensionless numbers. Concept 2. Dimensional homogeneity. All terms in an equation must be dimensionally homogeneous. For example, in the equation given in basic physics classes that relates position or displacement, velocity, acceleration, and time, all of the terms in the equation must have the same dimensions. In the common case of an initial displacement, x0, an initial velocity, v0, and a constant acceleration, a, the displacement equals the initial displacement plus the initial velocity times time plus 1/2 the acceleration times time squared. Because the displacement is in units of length, all the terms must have the units of length. The initial displacement must also have units of length. Because t has units of time, v0 must also have units of length per time. Because t squared has units of time squared, the acceleration, or 1/2 the acceleration, must have units of length per time squared. Dimensional homogeneity makes it easier to figure out the units of a constant or parameter in an equation because you know that all of the terms in an equation must have the same units. We give further examples in What the Schmidt Examples. Principle 3. Arguments of transcendental functions. The arguments of transcendental functions, such as the sine, the cosine, the exponential, the log, and others, must be a pure number. In other words, it's a dimensionless number like we discussed earlier. Transcendental functions themselves are also dimensionless. You can often figure out the units of some part of an argument to a transcendental function from the fact that, overall, it must be dimensionless. For example, in the equation y equals sine of omega t, If t has units of time, then what are the units for omega? Omega t must be dimensionless, so omega must have units of inverse time. In the equation x equals x naught e to the negative at cosine of omega t, what are the units of a and omega? Since at and omega t are both dimensionless and t has units of time, a and omega must both have dimensions of inverse time. In the equation, capital T equals capital T naught e to the negative lowercase t over tau, if lowercase t over tau is dimensionless and lowercase t has dimensions of time, then tau must also have dimensions of time. Before we go on, it might be worth realizing that we don't have units for y, x, and x naught, or capital T and capital T naught. But if y has units of some sort, then there has to be an implicit dimension in front of sign. X and x naught must have the same units, and capital T and capital T naught must have the same units. One of the places that people sometimes get fooled by the fact that the argument of a transcendental function must be dimensionless is looking at the log base 10 term in decibels. Decibels is defined as 20 log 10 of the amplitude ratio, or 10 log 10 of the power ratio. Decibels, therefore, always contain the ratio of two numbers with the same units. However, sometimes the denominator is implicit. For example, in dBm, the denominator in the ratio is milliwatts, and in dBu, it's the voltage you'd have if you dissipated 1 milliwatt in a 600 ohm resistor, or approximately 0.7746 volts. So, if someone takes the dB of a set of measurements and they don't have an explicit reference unit in there, you can assume that they are using an implicit reference unit. In the companion video, What the Schmidt Examples, we give further examples of dimensionless numbers, dimensional homogeneity, and arguments of transcendental functions. The takeaways are 1. There are ways to combine variables or measured quantities to create dimensionless numbers, which can help reduce the measurements you need to characterize your system. 2. All the terms in an equation must have the same dimensions. In other words, equations must have dimensional homogeneity. 3. Arguments of transcendental functions must be dimensionless. And 4. Decibels often have an implicit reference or denominator used in their calculation. Thanks for watching. This video was brought to you by the DOFPro team.